4:10 p.m. Please bear with me. Okay. Okay. So those who have joined the class can give their attendance in the chat box. I repeat, those who have joined the class can give their attendance in the chat box. I repeat, those who have joined the class may give their attendance in the chat box. Today I will take class till 4:10 p.m. So please bear with me. Fine.
Okay, sir.
Okay. If you find that some portions or some slides of the first module is missing, please text me personally, then I will see to it. And if any fault is there, I will again resend the PPT.
Sir, actually the headings are showing, but there is no pictures below it.
Okay, let other people check.
Okay.
There might be a case that in your some problem may be there if other people can see those slides. So let me get clarify from the other people whether they are also facing the same problem or not. Okay. Can anyone respond whether my slides are visible or not?
Yes, sir, visible.
Okay.
Yes, sir. Visible.
So those who have attended the yesterday's lecture, they might be knowing that yesterday I have started the second module of this course, and we have started the very first topic of the second module, that is determination of stiffness matrix by potential energy approach. And we have solved one problem. We have solved this first problem, and in this first problem yesterday we have understood that how we can find out the global stiffness matrix for the entire problem by potential energy approach. Today we will continue the same topic by solving some more complicated problems. So let us solve the third problem first. Second problem I will show you later on. It is a little bit easy. So let us solve the third problem first. Fine. So I am reading the problem. You just listen it carefully. What the problem is telling to us. The problem is derive the global stiffness matrix for the three carts interconnected by a system of linear elastic springs shown in the figure by the principle of minimum total potential energy approach. That means for this entire spring cart system, what is the overall global stiffness matrix that I need to determine by using the principle of minimum total potential energy approach. I know that if I want to use this principle, first of all, I need to determine the total potential energy of the complete system. If you see in this system, three carts are there. This is cart number 1, cart number 2, and cart number 3. Assume these three carts to be the nodes. Assume these three carts to be the nodes. And there are total 5 elements are present in the problem. That means 5 springs are there. All these 5 springs are what? They are element. So this is first spring. This is the first element which is connected with the fixed end as well, which is connected with the fixed end and with the first nodal point. This is the second element connected between node 1 and node 2. This is the third element connected between node 1 and node 3. This is fourth element connected between node 2 and node 3, and this is fifth element which is also connected between node 2 and node 3. So is it clear? In this problem there are total 5 elements. This is element number 1, element number 2, element number 3, element number 4 and element number 5. And how many nodes are present? That is first node, second node, third node, and obviously this is also a node, but at this nodal point there will be no deflection of spring because this end is fixed. So we can say that total 3 nodes, first, second, third and this fourth node. And this fourth, this is node number 4, and it is also given in the problem that at node 1 the nodal displacement is u1, at node 2 the nodal displacement of the element is u2, at node 3 the nodal displacement is u3. Similarly, at node 1, 2 and 3 nodal forces acting along positive x direction are f1, F2 and F3. By the help of, or by using the concept of the principle of minimum total potential energy approach for the entire problem, what is the global stiffness matrix that I need to determine? Now, is the problem clear to all of you? Any doubt in the problem?
Yes, sir.
Other people, please respond whether any doubt is there or not.
No, sir. Understood.
Okay, so the very first step, we know that when we have to use the concept of total potential energy approach, the very first step is what? The very first step is calculation of potential energy pi or potential function. It is also known as potential for the entire system. And I know that the potential energy is given by, it is what? It is nothing but the summation of internal energy as well as the summation of external energy. And we know that internal energy is nothing but the total strain energy stored in this given spring cart system. And what is W? W is the work done by the external forces acting on this spring cart system. From the diagram, it is very much clear that F1, F2 and F3 are the external forces acting at nodal point 1, 2 and 3. So first of all, what we will do, we will find out the expression of U, then we will find out the expression of W, we will put the expression of U and W in equation number 1, then we will get the total potential energy of the system. And since I have to minimize the total potential energy, that means in order to minimize this total potential energy, what I need to do? I need to partially differentiate this potential energy expression with respect to which value? With respect to this displacement, because throughout the problem this u1, u2 and u3 is changing due to the application of nodal force f1, f2 and f3. That means first time del pi by del u1, that we will equate it to 0, we will get one equation. Second time del pi by del u2 equal to 0, again we will get one equation. Third time del pi by del u3 equal to 0, again we will get that third equation. Then those three equations we will write in matrix form, and then we can get our global stiffness matrix. So is the entire procedure clear for this problem?
Yes, sir.
Okay, so let us find out the total strain energy stored in the spring cart system. We know from the previous few classes, I have told you in some 2-3 classes back, that if in a system, that is, if in a system a spring is present, if in a system a spring is present and if that spring is subjected to some external force F, then due to removal of this spring force F, what will happen? The spring will come back to its initial position, by which, that means how it is coming, it is having some strain energy stored in it, and that stored strain energy is given by the expression U is equal to half into stiffness of the spring K into square of deflection of the spring. This is the expression of strain energy present in any spring member. Fine, U is equal to half K into delta square. So if I see this problem, there are total 5 spring elements are present. Then the expression for this strain energy will be what? It will be U equal to, and let us assume that the linear displacement of this first spring element is delta 1, of the second spring element is delta 2, of the third spring element is delta 3, fourth spring element is delta 4, and fifth spring element is delta 5. Then I can write U is equal to what? I can write U is equal to half K1 delta 1 square for first element plus half K2 delta 2 square plus half K3 delta 3 square plus half K4 delta 4 square plus half K5 delta 5 square, which is equation number 2. Is it okay so far?
Yes, sir.
Okay, other people please respond whether it is
Yes,
okay
sir.
or
Yes, sir.
not. Okay, so where delta 1, delta 2, delta 3, delta 4 and delta 5 are what? They are deflections of these 5 springs. Fine. So if I want to evaluate the value of total strain energy, first of all, I need to determine the value of this linear deflection. So let us find out. Linear deflection will be nothing but the linear displacement of the spring due to the external force acting on it. Fine. So if I assume if this is my node 1, this is my node 2, this is my node 3 and this is my node 4, that is fixed end. I know that in this fixed end the deflection, that is U4, will always be 0. Fine. Then for for first element, this deflection delta 1 will be how much? It is nothing but equal to U1, because at this end I am applying a force F. Due to this force F, this element can displace a length of U1. So deflection delta 1 for first element will be equal to U1. Yes or no?
Yes, sir.
Okay. Similarly, that is, this is my second element, which is connected between, which is having one node, whose one node is 1 and the second node is node 2. So, and if you see in node 2, nodal force F2 has been applied, and in node 1, nodal force F1 is applied. If you see the entire system has a tendency to move in right direction. The entire system has a tendency to move in this direction. Then I can assume that F2 is greater than F1. Due to F2, deflection in the spring is U2. Due to F1, deflection in the spring is U1. Then overall deflection delta 2 for the second element, if F2 is greater than F1, will be equal to U2 minus U1. Is it okay? This delta 2, expression of delta 2, any doubt?
Sir, why delta 4 is 0?
Who is asking?
Sir, Niladri, why delta 4 is 0?
Why delta 4 is 0? For that, you please check my Google Classroom recorded lectures. This I have told in the very, I think some 4-5 lectures back I have told you. Since you are attending the first class, so for you I will not discuss the same things again and again. Please see my
Okay,
recorded lectures, then you will come to know.
okay, sir.
Okay. So is this expression clear? Delta 2 is equal to u2 minus u1.
Yes, sir.
Okay.
Yes, sir.
Similarly, for the third element, this is my third element. Fine. And I can see that third element is connected from node 1 to node 3. At node 3, force present is F3. Deflection of node 3 is U3. At node 1, nodal force is F1, deflection is U1, and the entire element has a tendency to move towards right direction. Then I can assume that F3 is greater than F1. If F3 is greater than F1, then this delta 3 will be U3 minus U1. This delta 3 will be U3 minus U1. Yes or no?
Yes, sir.
Fine. Delta 3 will be U3 minus U1. So delta 3 is U3 minus U1. Fine. Similarly, delta 4, that is deflection for the fourth element. I can see that the fourth element is connected from node 2 to node 3, and the entire system is moving towards right. That means force F3 is greater than force F2. If that is the case, then deflection delta 4 value will be how much? Can anyone tell me what will be the value of delta 4?
Sir, U3 minus
Yes,
U2.
it will be again U3 minus U2. Is it clear? It is U3 minus U2. Any doubt in delta 4? Hello? Is it clear?
No, sir. No, sir.
Okay. Next is fifth element. I can see that fifth element is connected from node 2 to node 3. Again, the entire system has a tendency to move towards right direction. That means I can assume that F3 is greater than F2. If F3 is greater than F2, then for this element 5 also, delta 5 also, it will be U3 minus U2. Is it clear?
Yes, sir.
Fine. So let this is be equation number 3. Let this is be equation number 3. Then what I will do, I will substitute the values of delta 1, delta 2, delta 3, delta 4 and delta 5 in equation number 2. I will get one expression of u. And that expression of u is this equation number 5. Okay? Any doubt in equation number 5?
Okay. No, sir. No,
Hello?
sir.
Okay. So I have calculated the value of strain energy stored in this spring cart case. Next is I am left with this value, that is work done due to external forces. Again, if you remember some 2-3 classes back, I have told you that work done due to external forces has three components. One component is due to traction force, that is UDL. Second component is due to surface load or surface force or body force, and the third component is the point load. So if I see this problem, in this problem, which force is acting? That is, the point load is acting. Neither any UDL is present in this problem nor any body force is present. Fine. So, and I know that when a point load is present, then this external work done is given by the relation, that is W is equal to summation of, what is the formula of work done? Force into displacement, that is force F into displacement UI. I means I represents the node where this point load is being applied. That means in this problem there will be total 3 work done due to point forces, that and this work done will be, and I know that this value of work done is always negative in nature, so W will be minus, this is that work done F1 U1, that is 1 into u of I. Now this, it is acting at nodal point 1, so it will be u1, f1 u1 minus this point load, that is f2 into u2, minus at third point this point, this work done due to point force, that is f3 into u3. So this is the expression of w, that is minus f1 u1 minus f2 u2 minus f3 u3. Equation number 3, equation number 4. Is the equation number 4 clear?
Yes, sir.
Okay, since we got the value of u, we got the value of w, what we will do is we will substitute equation 5 and equation 4, that is values of u and w from 5 and 4 in 1. Then I will get the total potential energy for this spring cart system. And this total potential energy is given by this expression, that is u
Excuse me, sir.
plus this expression, that is w. Yes,
Sir, in external work done, why negative sinus comes?
this also I have discussed 3 to 4 lectures back, so please refer my recorded
As
lectures
it
in
is
Google
external
Classroom.
thing, that's why. As it
Yes,
is
it is an, see, it is an external force, you are doing it on the system, so as a sign conventions we are taking it negative.
okay, okay, sir. Thank you,
Fine,
sir.
okay. So this is 5 plus 4. This is equation number 6. That is 5 plus 4. Half k1 u1 square plus half k2 u2 minus u1 whole square plus half k3 u3 minus u1 whole square plus half k4 u3 minus u2 whole square plus half k5 u3 minus u2 whole square minus f1 u1 minus f2 u2 minus f3 u3, which is equation number 6. Is it clear? Equation number 6.
Yes, sir.
Other people, please respond whether it is clear or not. Others, please respond whether it is clear or
Yes,
not.
sir.
Okay. So now I have to apply the principle of minimum total potential energy. According to this principle, I need to minimize the value of total potential energy of the system. How I can minimize? If I partially differentiate this equation number 6, if I partially differentiate this equation number 6 with respect to the variable quantity, which is in the problem is displacement ui, and if I equate it equal to 0, then the value of pi will be minimum. Since there are 3 nodes present, first, second and third node, and on first node displacement is u1, on second node displacement is u2, on third node displacement is u3, so this I varies from 1 to 3. That means first time you will partially differentiate with respect to u1, second time with respect to u2, third time with respect to u3. Is the step clear?
Yes, sir.
Fine. So let us differentiate, partially differentiate equation number 6 with respect to u1. I am just skipping the steps because only differentiation is there. You can easily do the partial differentiation. Fine. You have to open these brackets. This is a minus b whole square. That is a square plus b square minus 2ab, and just differentiate it. So if you partially differentiate equation number 6 with respect to u1, you will get equation number 7. That is k1 plus k2 plus k3 times of u1 minus k2 u2 minus k3 u3 equal to f1. Similarly, if you partially differentiate equation number 6 with respect to u2 and equate it equal to 0. That means del pi by del u2 equal to 0, you will get equation number 8. And when you partially differentiate equation number 6 with respect to u3 and equate it equal to 0, you will get equation number 9. Is it clear? I have skipped the steps. Why? Because in yesterday's class, when I was solving the first problem, I have shown you all the steps. Fine. So no need in. So every time if I write all these steps, then it will take some. It will take some time. So better these calculations you can do. You can do these differentiations. Fine. So you will get equation number 7, 8, and 9. So far it is clear. Equation 7, 8, and 9. Fine. Okay. So if you see the governing algebraic equation for this problem is what? Governing algebraic equation for this problem is f is equal to k into delta. Obviously here delta is in terms of u, so I can write k into u is equal to f. How I know that the governing algebraic equation is f is equal to k into u? Because I know that for a spring system, if you apply an external load, this force F, then after some time the spring will come back to its original position by the same value of this force F, and this force is known as your restoring force, which is given by the expression minus k into u. If I assume that u is the linear displacement along this direction, fine. So we are ignoring the minus sign and we are taking only the magnitude. So that is f is equal to k into u. Now we can write this expression f is equal to k into u in matrix form as matrix k into matrix u equal to matrix f. And what is this matrix k? This matrix k is known as global stiffness matrix for the entire problem. Global stiffness matrix. Global stiffness matrix for the entire problem, and this is what I have to find out in this particular problem. See, derive the global stiffness matrix. What is this u? This u is known as, this u is your what? This u is nodal displacement vector. This is nodal displacement vector. That means there are total 3 nodes are present. So this u will be a column matrix, 3 cross 1 column matrix. And what is this f? This f is known as nodal force vector. This f is known as nodal force vector. Fine. So I can write like this, since you can see that in this particular problem only 3 nodes are present. So this nodal displacement vector is a 3 cross 1 matrix. That is 3 rows and 1 column, u1, u2, u3, equal to, again this nodal force vector is also a 3 cross 1 matrix. That is 3 rows and 1 column. That is 3 forces acting on the 3 nodes of the element. That is F1, F2, F3. And if you remember in the last lecture, when I was discussing the first problem, I told you that what will be the order of this global stiffness matrix? Order of this global stiffness matrix will be equal to the number of node present in this problem. In this problem, there are total 3 nodes present. I should say total 4 nodes present. That is first node, second node, third node, and the fourth node. Since the fourth node is having zero displacement, so I will not consider this node. So I can say that total 3 nodes are present in this entire problem. So the order of this stiffness matrix will be a 3 cross 3 matrix. That means 3 rows, 3 columns. The first row represent the first node, second row of the matrix represents the second node, the third row of the matrix represents the third node. Similarly, first, second and third column represent that particular node in the given element. Fine. So this is for first node, this is for second node, this is for third node. So I have written C 1, 2, 3, 1, 2, 3. Now I have this expression. Now I have to convert this equation 7, 8 and equation number 9 in matrix form. So I can say that if this is the first row, then this first row comprises of yes, I can write that this first row is of u1, second row consists of is of nodal point u2, third row is nothing but nodal point u3, first column is nodal point u1, second column is nodal point u2, third column is nodal point u3. So I can write, see, coefficient of u1 is what? K1 plus K2 plus K3. Coefficient of u2 is minus K2. Coefficient of u3 is minus K3, which is equal to F1. So corresponding to F1 along this row, I will write K1 plus K2 plus K3, K1 plus K2 plus K3 for u1, then minus K2 for u2, see minus K2 for this u2 and minus K3 for u3, see minus K3 for u3 into u1, u2, u3 equal to F1, F2, F3. Similarly, for second expression, this is equation number 8, F2 equal to this expression. So F2 equal to this expression, that means this value will be what? Coefficient of u1, this value will be coefficient of u2, this value will be coefficient of u3. So let us check. So minus K2, minus K2. Then K2 plus K4 plus K5 for coefficient of u2, K2 plus K4 plus K5 coefficient of u2. Then minus in bracket K4 plus K5, sorry, minus in bracket K4 plus K5 coefficient of u3, see, minus K4 plus K5 coefficient of u3. Then the third row, for the third row, this is that equation number 9. I have to write it in matrix form. This is the coefficient of u1. This is the coefficient of u1. This is the coefficient of u2. And this is the coefficient of u3. So in row, I will write minus k3, then u2, that is k minus in bracket k4 plus k5, minus in bracket k4 plus k5, and then the third one, that is for u3, k3 plus k4 plus k5, that is c k3 plus k4 plus k5 into column matrix u1, u2, u3 equal to fourth matrix f1, f2, f3. Now you can cross verify it also whether the matrix which you have generated is correct or not. For that, what you need to do? You need to do the matrix calculation. So this expression, how this equation number 7 will come if you do the matrix multiplication. That means this first row into first column multiply. That means K1 plus K2 plus K3 into U1. See, K1 plus K2 plus K3 into U1. Then minus K2 into U2. See, minus K2 into U2. Then minus K3 into U3. Minus K3 into U3 equal to F1. Like that means this first row is correct. Likewise, if you check for equation number 8 and equation number 9, equation number 8 and 9 is also correct. So finally, for this particular problem, the global stiffness matrix is this expression, and which is nothing but this matrix. If in the question it has been told to you that also find out the nodal displacement vector and the nodal force vector, this is my nodal displacement vector, this is my nodal displacement vector, and this is my nodal force vector. With this problem is complete. Is it okay? Any doubt in this problem?
Sir, if there is more than 5 or 6 nodes, then we have to make a 5 by
Yes.
5.
Say if in a problem, say if in the same problem, if I attach two more cards and if I attach two more element, so there will be a total 5 node. If there is a 5 node, then this K matrix will be 5 cross 5 matrix, 5 rows, 5 column.
But sir, if there is no, I mean, if you are adding nodes and if there is no elements, I mean, if you are not adding elements, so like
If you
then
are
what?
adding, if you are not adding any element, then that particular value will be 0, because if there is no element, definitely if there is no spring element, definitely there will be no value of stiffness. Then in that case I will write 0, I will write 0 in that particular place, but normally it will not be there. If node is present, definitely element will be there, because an element comprise of two nodes. If node is there in the problem, that means definitely element will be there. Without element, node is incomplete. Without node, element is incomplete. Is it okay?
Yes.
Other people, please respond whether the problem is clear or not.
Yes, sir.
Yes, sir. Yes, sir.
Is it clear? Okay, I
Yes, sir.
think Krishanu and okay, wait. I think that Krishanu and Alok, Krishanu, Alok, Orko, you haven't attended my yesterday's class. So it will be little bit difficult for you, since Akash has attended yesterday's class.
Sir, I have
I
seen
am
the
doing the
video.
same procedure. Hello?
You, I have seen the video you
You
posted.
have seen the video. I am just following the same procedure. Only the
Yes,
problem
sir.
is different. Only the problem is different. I have taken a little bit more complicated problem. In the last lecture, that means in yesterday's class, the problem was very simple. Only three spring elements were there. All the three elements were in series, and at all the nodal points forces are present. Here I have, in this problem, what I have did, I have just changed the diagram of the problem. I have added some more elements and I have made the problem little bit complicated. Regarding the or else the entire process is same. There is
It
no change in
consists
the
of
process.
parallel as well as series.
Yes, yes, yes. They have that means if you can see K4 and K5 are in parallel. K1 and K2 is in series. But if you see this K3, combination of K4, K5 and K2 are in parallel. Fine. So in the problem which I have discussed just now, this is a little bit tricky problem, but process is same. Is it clear?
Yes, sir. Yes.
You can expect such kind of problems in exams also. Fine.
Sir, I
Okay.
have one question, sir. So can I ask?
Who is asking?
Sir, Akash.
Akash. Okay, yes, you can ask.
Sir, if the forces are in different direction, means
If
suppose
the
if
forces are in negative x direction, you have to put minus f1.
okay,
Then in that case, it is very
displacement
obvious. This will be minus f1, minus f2, minus f3.
and sir displacement also change now. Then
Yes, if see, if you are taking plus x direction to be the positive, you have to take minus x direction to be negative.
yes, sir.
Then body will not be in equilibrium if you don't take it. Similarly, if any force or if any displacement is along positive y and negative y direction, you have to take the sign conventions
Yes,
that you
yes.
know already. You are doing it in strength of material also. You have did it in
Yes.
machine design also.
Okay, sir.
Okay. So
Thank you, sir.
is the problem clear to all of you? This problem? Any doubt in this problem?
No, sir.
Okay. I will take 10 more minutes of you and I will solve one more problem. Then you all can leave the class. This problem is a little bit easy problem. So that's why I have taken the third problem because it is a little bit complicated problem. So now let us solve the second problem. Fine. Let us solve this second problem. Now you will solve this problem. I will just give you hint and you have to answer me. Since you have understood the process, how we are using the concept of potential energy approach to find out the global stiffness matrix, the load vector matrix and the nodal displacement vector matrix. So this problem you will solve. Just I will give you the hints. Okay. Fine. So let us read the problem. The problem is for the linear elastic spring subjected to a force of 5000 Newton shown in the figure. This is a spring element. One end of the spring element is subjected to a compressive load of 5000 Newton. Okay, evaluate the potential energy. PE means potential energy. I have written in short. Evaluate the potential energy for various displacement values. Understand the problem. You have to evaluate potential energy for various displacement values and show that the minimum potential energy corresponds to the equilibrium position of the spring. That means you have to find out the minimum potential energy because for minimum potential energy the displacement value will be minimum and the entire system is in equilibrium. Also, you have to sketch the variation of potential energy with the spring deformation. That means the potential energy pi, which you will find out. It will be an expression in terms of x because here x is the deflection. Fine. So you have to take some values of x. For that, those particular values of x, you will calculate the values of pi and then you have to plot the variation of pi versus x. Is the problem clear to all of you?
Yes, sir.
Fine. So first of all, you tell me how many element and how many nodes are present in this problem.
Sir, one element and two node.
Yes. In this problem, there is only one element and we are having two nodes. Assume this is the first node, this is the second node, or this is the first node, this is the second node. Now, can you tell me by looking at the diagram, one nodal displacement will be zero. Which nodal displacement is zero? The bottom node displacement is zero or the top
The
node
bottom
displacement
one,
is
bottom
zero?
one.
Yes, the
Bottom.
bottom node displacement is zero. Why zero? Niladri, are you there?
Yes, sir.
Okay, now I am explaining your answer. You are telling no that why the fixed end node will be zero. Please listen to it carefully. If you apply this compressive load of 5000 Newton at this particular node, then definitely the spring will compress. Since this end is fixed, and spring has a tendency, spring is what? Elastic in nature. So after some time, what will happen? Spring will vibrate with decreasing amplitude. After some time, the spring will come back to its original position. Yes or no? How it is coming back? Due to the presence of restoring force, which is given by F is equal to minus kx. So that's why, see, if you apply either a compressive load or a tensile load, the spring will elongate, the spring will compress. But since this is fixed point, this is a wall. In this wall or in this fixed point, will you find some displacement? You will not find the displacement. Displacement is always zero. Now is it clear?
Yes, sir.
Okay. So that's why this particular at this node there will be no displacement. Only displacement will be at this node. And if I divide this particular element into 100 nodes, that means this is first, second node, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, all these nodal points will be having displacement except the 100th nodal point. Is it clear to all of you?
Yes,
Hello.
sir.
Is
Yes,
it
sir.
clear? Okay. So the first step is what? I have to calculate the potential energy of this particular problem. I know that potential energy pi is equal to strain energy plus the external work done in this problem. Strain energy will be what? Will be half k into x square, because in this case x is the deflection, so u will be half kx square. Since only one element is present, so u is half kx square. If there are more elements, then u will be half k1 x1 square plus half k2 x2 square and so on. Yes or no? In this element only one element is present. For that element displacement is x, so it is u equal to half kx square. Is it clear?
Yes, sir.
Fine. Next is I need to find out what? I need to find out work done by external force. Since in the problem it is very much clear that a point load is doing external work done on this element, and for external and for point load work done is what? Work done is summation of force into displacement. In this problem displacement is x, so I will write xi, that means acting at which nodal point. Fine. Since here this summation will not work because only one element is present, so w will be equal to f into x, at this nodal point. Fine. F into x. And I also know that this external work done is always negative, so w will be minus f into x. Is it clear so far?
Yes, sir.
Okay. Next, what I will do, I will add this x, I will put this value over here. I will put this value over here. I will get the value of final potential energy of the problem. And that final potential energy is given by pi equal to half kx square minus fx. See, half kx square minus fx. Is it clear? Equation number 2.
Yes, sir.
Fine. Okay. So since what we need to do, we have to use the concept of potential energy approach. We know that means if you are using the concept of potential energy approach, you have to keep this potential energy minimum. How you can keep? If you partially differentiate this potential energy with respect to the displacement of the problem, and if you equate it equal to 0, then you will get one value of x. That value of displacement x, if you put in equation number 2, your value of potential energy pi will be minimum. Yes or no?
Yes, sir.
Fine. So since in this problem only the displacement is present at this nodal point, so del pi by del x is equal to 0, or else I would have written xi. I means number of nodes where displacement is occurring. Only in this problem displacement is occurring at this nodal point, and this nodal point is fixed, so I will not consider this nodal point. So del pi by del x equal to 0. That means del by del x of this particular expression, half kx square minus fx equal to 0. Half is, you can take out of this del by del x operator, k you can take out of this del by del x operator. Del by del x of x square is 2x minus del by del x of fx. F you can take out of this del by del x operator. Del by del x of x is what? 1. So equation becomes half k 2x minus f equal to 0. This 2 and this 2 cancel out. So f is, if you take this f in right hand side, f is equal to kx, or x is equal to f by k. F is given in the problem, that is 5000 Newton divided by k. K is the stiffness of the problem, which is also given, that is 125 Newton per mm. So you will get the value of x coming out to be 40 mm. This is the value of displacement which you need to apply on this particular spring in order to keep this potential energy value pi minimum. That means pi will be minimum when you will substitute x equal to 40 mm in equation number 2. Yes or no?
Yes, sir.
So let us substitute and get the value of minimum potential energy. That is pi is equal to half into k. K is given 125 Newton per mm into x square. X is what? 40 square minus f. F is what? 5000 Newton into x. X is what? 40. See, I get the minimum potential energy value pi to be minus 1, 2, 3, 4, 5. That is minus 1 lakh Newton millimeter. This is the minimum potential energy. Or if I talk in terms of Newton meter, it will be minus 100 Newton meter. Is it clear?
Sir, here minus sign signifies what, sir? As it moving
Minus means
down.
minimum value, minimum. Potential energy is maximum, it is potential. Minus means you will come to know. You will come to know in the next slide. Fine. Minus means see, if I plot a graph between pi versus x for different values of x, I will evaluate different values of pi. See, this is the minimum value. At this value, potential energy is minimum. Yes or no?
Yes, sir. Yes, sir. Now I get it.
Okay. So is it clear? This minimum potential energy value pi minus 100 Newton meter. Any doubt in this? Hello. Any doubt so far?
No, sir.
No, sir.
Okay. So if you see now, next what is left? I need to plot a graph between potential energy with spring deformation x. That means for different values of x, I have to get different values of potential energy. How I can get? Say x varies from minus 100 to 100 and I am taking in multiples of in difference of 20, that is minus 80, minus 60, when x is minus 40, minus 20, 0, 20, 40, 60, 80. You can take in difference of 10, you can take in difference of 30, it's your choice, fine. So when x is minus 80, what is the value of pi? That means I know that pi is what? Pi is half k x square minus fx. Half k x square minus fx. K is 125 given in the problem. F is 5000 given in the problem. Now this x you have to vary. In the first case, in equation number 3, put x equal to minus 80. You will get the value of pi equal to 800. Second case, in equation number 3, put x equal to minus 60. In equation number 3, you will get the value of pi. Likewise, if you do it for 10 points or 15 points, these are the different values. And from this value, you can check that the potential energy is minimum at which point? It is minimum at x equal to 40 mm. It is minimum at x equal to 40 mm. So from this you can cross check whether you have did your calculation correctly or not. Fine. So now what you do, you take a suitable scale in x-axis, take a suitable scale along y-axis and just plot these values. If you plot it, you will get this kind of curve. You will get this kind of curve. From this curve, that means it is decreasing. This is the minimum value, and then from this point increasing. Fine. So from this graph, I understood that the value of potential energy is minimum when x equal to 40 mm, and that minimum value is minus 100 mm. Is it clear?
Yes, sir. Clear.
You also need to verify that this x equal to 40 mm is the equilibrium position for this particular problem. How you can verify? We know that del pi by del x is equal to 0 at which point? At x equal to 40 point. Del pi by del x is equal to 0. Del pi by del x is equal to 0 at which point? At x equal to 40 mm. We have calculated. So just differentiate this pi with respect to x. We have this equation, that is f is equal to kx, or I can write kx minus f. K is what? 125. F is what? 5000. X, we have already calculated the minimum value, that is 40 mm. Put 125 into 40 minus 5000. So this del pi by del x, which is nothing but kx minus f, at x equal to 40 is coming out to be 0. That means my this condition is satisfied. If this condition is satisfied, that means x equal to 40 mm will be the equilibrium position for this particular spring system in order to get the minimum potential energy. Is it okay? This problem, any doubt in this problem? Simple problem. कोई डाउट है
Yes.
किसी को इस प्रॉब्लम में?
Yes, sir.
No, sir. No, sir.
Other people, please respond whether any doubt is there or not in this problem. कोई डाउट किसी को इस प्रॉब्लम में?
No.
No, sir. No, sir.
Okay.
बट सर एंड में हम लोग को फिर से वेरीफाई क्यों करना पड़ रहा है? मतलब पहले तो हम
वेरीफाई इसीलिए करना पड़ रहा है. इफ यू सी दिस, इफ यू सी द क्वेश्चन, रीड द क्वेश्चन. इवैल्यूएट द पोटेंशियल एनर्जी फॉर वेरियस डिस्प्लेसमेंट वैल्यू एंड शो दैट दिस लाइन. Wait, right, show from the current slide. Wait, this line, and show that the minimum potential energy corresponds to the equilibrium position. That means this is my minimum potential energy, pi minimum minus 100 Newton meter. Fine. For this value of pi, what is the value of x for which the entire system will not move if you apply a force of 5000 Newton? So कैसे ये मूव नहीं करेगा? ये मूव तभी नहीं करेगा when del pi by del x is equal to 0. And initially we have found out that del pi by del x equal, when we have calculated del pi by del x and we have equated it to 0, we get that at x equal to 40 mm, when this displacement value will be 40 mm, then no more further deflection is possible. That means then I know that del pi by del x is kx minus f. So in place of x, I will substitute this 40. Fine. See, del pi by del x is coming out to be 0. So if del pi by del x is not 0, that means equilibrium condition has not been attained. So from this line, I understood that I have to verify at the last. I have to verify that whether this x equal to 40 mm is the equilibrium position of this particular problem or not. Is it okay?
yes sir.
Okay. So one more problem is left that we will do in the Monday's class. Monday I am having class, second lecture. With this, we will complete this first subpart of second module. Fine. Okay, if anybody is left to give your his or her attendance, you can give your attendance, or else you can leave the meeting. And Niladri, please be regular from next time onwards.
Sir, in classroom, sir, I have no data uploaded in the classroom. Maybe because I was detached, that's why. But I
Then
have no.
you can ask some of your friend. Krishanu, are you there? Alok, hello Alok.
Yes, sir. I'm here. Yes, sir.
Alok, can you please provide that Google Classroom code to Niladri so that he can join and he can see the previous
Yes, sir.
lectures?
Absolutely. I'm
Please give
giving.
it to him by today itself. You give it. Now only you give it, and please see the lectures. Okay,
Sure, sir.
Okay, sir.
Niladri. Okay, fine. Okay, Alok, if you are facing any problem, you just go through the previous class lecture, and if you are facing any doubt, you can ask me freely.
Yes, sir. Definitely, sir.
Okay,
Thank you,
okay.
sir.
Thank you. Then we will meet on Monday. Thank you. Thank you for listening.